Picture this. It is 2 in the morning.
Oh, the classic hour.
Right. You're sitting in the dark. The glow of your monitors is reflecting off your glasses, and you're just staring at your terminal.
We've all been there.
Yeah, exactly. And somewhere out there, maybe in this massive warehouse-sized data center out in the high desert, thousands of GPUs are just humming away in the dark.
Drawing enough power to light up a small city, yeah.
Right, processing literally billions of parameters,
Yeah.
calculating trillions of floating point operations every single second. And, you are a software engineer. You know how to write code that runs perfectly on your local machine.
Sure, spin up a container, write a script. Easy.
Exactly. But how on earth do you mathematically distribute a single massive artificial brain across thousands of separate physical computers without the entire system just crashing into a fiery heap of network timeouts?
It is basically the defining engineering challenge of our era because writing a script that runs locally is one thing, right? But orchestrating a supercomputer, that's a completely different reality.
Yeah.
We're basically fighting a two-front war here. On one side, you have memory limits. And on the other side, you've got compute bottlenecks.
Yeah, the classic constraints.
Right, and every single architectural decision we're looking at tonight is essentially born out of those constraints.
And that is exactly what we are getting into for this deep dive. We're pulling from a seriously thick stack of engineering white papers and architecture notes on LLM mastery tonight, specifically tackling how to scale AI models across hardware.
Yeah, it's fascinating stuff.
Our mission here is to map out the major categories of scaling, so data parallelism and model parallelism, so you can actually understand the distributed systems architecture required to train massive language models.
Right, because these aren't just like neat theoretical tricks. These are the literal weapons we use to break through the physical limits of silicon and copper.
Exactly. So let's unpack this from the ground up. Before we get into the really mind-bending ways of slicing a neural network into pieces, let's look at the most straightforward distributed systems approach. In our notes, this is called data parallelism.
Right, and the core concept of data parallelism is that you replicate the entire model onto every single GPU in your cluster, but you split the data itself.
Okay.
So you leave the architecture of the neural network completely intact.
Right. To put that into perspective, imagine you're managing a massive data entry project and you hire, say, 100 workers.
Okay, 100 workers.
You give every single employee the exact same instruction manual. That manual is the full AI model, complete with all its rules and parameters.
Makes sense.
But you hand them different stacks of paperwork to process. That's the training data. So worker A gets documents 1 through 10, worker B gets 11 through 20, and so on. They all follow the exact same rules, but they're crunching different raw material.
From a software engineering standpoint, it's actually incredibly elegant. I mean, you basically just wrap your model in a distributed data parallel module.
Right.
Each GPU runs a forward pass on its unique slice of the data, calculates its error, and then runs a backward pass to calculate the gradients.
Which is basically figuring out how the model needs to change to get smarter, right?
Exactly. But, and this is but there's a massive distributed systems challenge lurking right there.
Yeah.
They all have to synchronize.
Because if GPU 1 learns something from a document about quantum physics, and GPU 2 learns something totally different from a document about French poetry.
They have to reconcile that knowledge.
Right. They have to get on the same page and update their instruction manual simultaneously before picking up the next stack of paperwork.
Exactly. And the mechanism they use to do that is this network communication protocol called all-reduce. And it's not as simple as just, averaging numbers together.
I would imagine not.
Yeah, because if you have 10,000 GPUs all trying to shout their updates to a central server at the exact same microsecond, you'll create a massive network bottleneck.
Oh, the switch would just melt.
Completely melt. So engineers use architectures like ring-all-reduce, where the GPUs arrange themselves in a logical circle. GPU 1 passes a fraction of its gradients to GPU 2. Then GPU 2 adds its own and passes it to GPU 3, and this just streams around the ring.
Yeah.
It maximizes bandwidth and prevents any single point of network failure.
Okay, that solves the synchronization problem brilliantly. But I'm looking at the hardware specs in these white papers, and I'm seeing a hard physical wall approaching.
Oh, yeah. The memory wall.
Right, because as a software engineer, you know that models are growing exponentially. We went from millions of parameters to billions, and now we're regularly dealing with trillion parameter models.
And that is exactly where data parallelism simply breaks down. Let's look at the physical limits for a second. An NVIDIA A100 GPU might have, say, 80 gigabytes of high bandwidth memory.
Which sounds like a lot.
It does, but a 70 billion parameter model just to load its weights in the optimizer states, that takes up way more than 80
Oh,
gigabytes.
wow.
Yeah, so you try to load that full instruction manual onto a single worker's desk, and you immediately get the dreaded out-of-memory error. The code crashes before you even pass a single byte of training data.
Because data parallelism requires every single GPU to hold a 100% full copy of the model.
Exactly. When the model gets bigger than the chip, you are dead in the water.
That's the ultimate scaling wall. I mean, you could have a cluster of 20,000 GPUs, but if the model can't fit into the memory of just one of them, the whole multi-million-dollar data center is basically useless to you.
Yep. So we can't just copy the model anymore. We have to physically chop the model up into pieces.
Which forces us to evolve our architecture. And this is where we move from data parallelism to model parallelism. Started with a strategy called pipeline parallelism. Our sources describe this as basically splitting the layers of the model across the GPUs.
Right, because a neural network is fundamentally just a deep stack of mathematical layers. Data goes into layer 1, gets transformed, passes to layer 2, gets transformed again, and so on.
So instead of cramming all those layers onto one chip, we build a literal assembly line. You put layer 1 on GPU 1, layer 2 on GPU 2, and layer 3 on GPU 3.
And that bypasses the memory limit entirely. Like if your model takes up 300 gigabytes of memory and you only have 4 80-gigabyte GPUs, you just divide the model into 4 sequential chunks.
And now everything fits comfortably.
Exactly. GPU 1 handles the early processing, passes its intermediate results, which we call activations over the network cable, to GPU 2, which does the next phase, and so on. You've basically turned the neural network into a distributed relay race.
Okay, but if I'm looking at this from a distributed systems perspective, I'm seeing a pretty glaring inefficiency here.
Oh, absolutely.
Like if node A is crunching layer 1 and node B is just sitting there waiting for the results so it can start layer 2, isn't node B effectively idling?
It is completely idling.
It's like having a microservice just hanging open, waiting on a really slow database query. In a world where data center compute time costs thousands of dollars an hour, having your most expensive hardware just sitting there empty-handed seems like a massive flaw.
It is a massive flaw. In the literature, this is known as the bubble problem.
The bubble problem.
Yeah. If you look at a Gantt chart or a timeline of GPU utilization during naive pipeline parallelism, you see these huge, empty pockets of time bubbles where compute is completely wasted.
Wow.
GPU 1 works while the others wait. Then GPU 1 passes the data and goes idle while GPU 2 works. It's heavily sequential, which is, the absolute enemy of parallelism.
Yeah.
At any given microsecond, only a fraction of your silicon is actually crunching numbers.
So how do we fix it? Because we clearly aren't just letting these million-dollar machines sit idle for 75% of the training run.
We solve it with a software engineering technique called microbatching.
Okay, microbatching.
Right. Instead of sending one massive gigabyte-sized chunk of data down the assembly line, which creates that massive delay, we take that batch and slice it into much smaller sequential slivers.
Okay, so instead of dropping one giant shipping container onto the conveyor belt and waiting for it to reach the end, you're putting a steady stream of small boxes onto the belt.
Precisely. You send the first microsliver into GPU 1. As soon as GPU 1 is done processing layer 1, it passes that sliver to GPU 2.
Right.
But instead of GPU 1 going idle, it immediately grabs the second microsliver from the data loader and starts processing that.
Ah, I see. So by the time the first microbatch reaches the final GPU in the pipeline, every single GPU behind it is actively chewing on a subsequent microbatch. You keep the entire pipeline saturated with data.
Exactly. You still have a tiny bubble at the very beginning of the process while the pipeline fills up, and a tiny bubble at the end when the last batch drains out. But you've reduced the wasted compute from a catastrophic failure down to a highly acceptable margin.
That's brilliant.
Yeah, you've kept the hardware fed, and you solved the memory issue.
So microbatching keeps the assembly line moving. But what happens if we hit a scenario where a single layer of the neural network is so mathematically massive that it instantly ohms a single GPU before it can even pass it down the pipeline?
Yeah, that's the nightmare scenario.
Because you can't pipeline a layer that's bigger than the chip itself.
Yeah.
Or what if we just need the mathematical operations within a single layer to happen insanely fast?
That's the exact edge case that breaks pipeline parallelism. And it brings us to the third strategy in the white papers, which is tensor parallelism.
Okay.
This is the microslice. Instead of splitting up the sequential layers of the model, we are fracturing the individual matrix operations themselves.
I was trying to visualize this earlier, and rather than something weird like, I don't know, multiple chefs trying to chop the exact same carrot.
Right, which sounds dangerous.
Yeah, totally. I was thinking about it more like two chefs working on the exact same giant sheet of pastry dough.
Oh, I like that.
Chef A is rolling out the left side of the dough while Chef B is rolling out the right side. They have to watch each other's hands constantly, matching their movements perfectly. Otherwise, they tear the dough right down the middle.
That analogy works perfectly because if the synchronization isn't instantaneous, the whole operation falls apart.
Mm.
A neural network layer is fundamentally just a giant matrix multiplication.
Yeah.
You're taking a massive grid of numbers and multiplying it by another massive grid of numbers.
Right.
In tensor parallelism, you take that grid and you physically slice it. You assign the left half of the columns to GPU A and the right half of the columns to GPU B. They both do the heavy math on their specific slices simultaneously.
But to get the final answer for that single layer to finish rolling out the pastry dough, they have to combine their results before the data can move forward to the next step.
Exactly. Constant, real-time communication. This isn't like All-Reduce where they sync up at the end of a long batch.
All right.
This is mid-calculation. They have to scatter the data, compute their halves, and then gather the data back together to form the complete output tensor. And this is where software engineering slams face first into the brutal reality of physics.
Let me guess. Network latency.
Yep.
Because if you've ever dealt with a microservice timing out because of a bad API call or a slow network switch, imagine that happening millions of times a second.
Exactly. If GPU A and GPU B are connected by a standard Ethernet network, or even like a fast InfiniBand network across a data center, the microsecond delay in sending those numbers back and forth will completely destroy your training speed.
The latency literally becomes the bottleneck.
Yes. Your GPUs will spend 99% of their time waiting for network packets to arrive, and maybe 1% of their time actually doing math.
Which explains a very specific constraint mentioned in the notes. They specify that tensor parallelism almost always happens strictly within a single node,
Right.
meaning one physical server chassis.
Yes. You might have 8 GPUs bolted into a single server box, and they can't just be wired together using the standard PCIe lanes on the motherboard either.
Really?
Yeah, those lanes are too slow for this kind of traffic. They require ultra-fast proprietary interconnects like NVIDIA's NVLink.
Oh, right, NVLink.
And NVLink isn't a network cable. It's essentially a massive high-bandwidth data highway soldered directly onto the board, allowing these GPUs to share memory and pass results back and forth at hundreds of gigabytes per second.
That's insane.
It really is. It's hardware and software co-design at its absolute peak. You're slicing a mathematical equation across physical silicon, relying on those physical copper pathways to ensure the latency is practically zero.
It's wild to think about. You're just typing Python code in PyTorch, but beneath the surface, your matrices are being physically fractured across separate physical chips and fired back and forth over these microscopic highways.
It's basically magic.
It really is.
Yeah.
But looking at the scale of modern models, things like GPT-4 or the massive open source models, it's clear that none of these strategies alone are enough. You can't just say, we'll use pipeline parallelism and call it a day.
Oh, definitely not.
To build the biggest models in the world, you have to combine them all into this massive orchestrated system. And that brings us to what the notes call 3D parallelism.
Yeah, 3D parallelism is where you orchestrate everything we just talked about into a perfectly tuned, multi-layered architecture. You have to map each software strategy to the appropriate physical hardware hierarchy in the data center.
Oh.
It works exactly like a Russian nesting doll. Inside the single server box, where you have those ultra-fast NVLink connections, you use tensor parallelism to slice up the biggest, most complex matrix math.
Because that's the only place where the communication speed is actually fast enough to handle the constant mid-calculation chatter.
Right. Then you step out of the box, you use standard high-speed networking cables to connect that server to the other servers in the rack or to the next rack over.
Yeah.
Across those connections, you use pipeline parallelism.
So sending the layers down the line.
Exactly. You send the first few layers of the model to server rack A, the next layers to server rack B. The communication requirements are lower because you only pass data at the end of a layer, not in the middle of it.
Okay, so we have tensor parallelism inside the box and pipeline parallelism between the boxes. Where does data parallelism fit into this 3D map?
So you take that entire pipeline, that whole sequence of server racks, and you duplicate the entire physical setup across your data center. Yeah. You have supercluster 1 processing training dataset A and supercluster 2 processing training dataset B. That's data parallelism on a macro scale. You're
Oh.
operating across three different dimensions of distributed architecture simultaneously just to keep the hardware fed and the model growing.
That is a beautiful, clean 3D architecture, but the white papers actually throw a wrench into it right at the end.
They always do.
Yeah. A fourth dimension, if you will. Expert parallelism for MOE, or mixture of experts models.
Right, Bowie.
Now, for you listening, a MOE model basically means that instead of one giant, dense neural network that fires every single parameter for every single word, the model is composed of specialized subnetworks.
Right.
You might have it. It says, this is a Python keyword, send it to the coding expert.
And it's highly efficient because you only activate a fraction of the model for any given prompt, which saves massive amounts of compute.
But my question is, how does this impact our pristine 3D network topology?
Yeah, it ruins it.
Right. Like, if different expert parts of the model live on completely different physical GPUs across the data center, how do you stop the network from imploding?
It's a huge issue.
What if 10,000 users suddenly hit the API asking for Python code at the exact same second? Does the coding expert GPU just catch fire while the French grammar GPU sits there completely idle?
Yes. That is known as the hotspot problem. In standard 3D parallelism, the flow of data is totally predictable. It's a steady river flowing from layer to layer.
Right.
But in MOE models, the flow of data is entirely dependent on what the users are asking for or what the training data happens to contain at that exact microsecond.
Which is random.
Completely. If the routing algorithm sends 90% of the network traffic to one specific GPU because it holds the most relevant expert, that GPU becomes a massive bottleneck. The entire distributed system, literally thousands of other GPUs, just grinds to a halt, waiting for that one chip to finish processing the Python requests.
So how is that solved? Because MOE models are the current state of the art, so they clearly figured out a way to manage the traffic.
They manage it through rigorous dynamic load balancing at the routing layer. The router isn't just looking at which expert is mathematically best for the token. It's also constantly monitoring the buffer capacity of the GPUs.
Oh, interesting.
Yeah, if the primary coding expert's queue is full, the system might have duplicate experts stored on other nodes, or it might force the router to send the token to a slightly less specialized, but currently idle expert.
So it's like managing a massive call center.
Exactly.
You want to route the tech support call to your absolute best engineer, but if they have 100 people on hold, you route the call to the next available agent just to keep the queue moving.
Perfect analogy. And if the queue gets too extreme, MOE architectures will actually employ a technique called token dropping.
Wait, really? Just dropping the data?
Yep. If a specific expert is completely overwhelmed and there's nowhere else to send it without stalling the whole supercomputer, the system might just drop the token entirely and move on, relying on the sheer scale of the rest of the model to compensate for the lost data.
Wow.
It is a constant, real-time traffic control nightmare happening at the microsecond level just to prevent those hardware meltdowns.
We have covered a massive amount of ground here. I mean, we took this journey from the frustration of a local 80-gigabyte memory limit all the way to orchestrating thousands of machines.
Quite the leap.
It really is. We looked at data parallelism, the simplest path of replicating the model and splitting the data, relying on all reduce to keep everything synced. Then we looked at pipeline parallelism, physically slicing the model into layers to build an assembly line, using micro-batching to eliminate those idle bubbles.
All right.
Then we zoomed in to tensor parallelism, fracturing the actual matrix math across GPUs on the same motherboard using ultra-fast NVLink highways. And finally, we zoomed out to 3D parallelism and expert parallelism, mapping all these software strategies onto the physical layout of the data center and dynamically routing traffic to prevent hotspots.
It's intense.
Scaling AI isn't just about plugging in more hardware. It's this delicate, high-wired dance of hardware and software co-design.
The incredible thing is, we're not even done scaling.
Not even close.
Like, if you think slicing up the matrices is intense, wait until we mess with the fundamental numbers themselves. Tomorrow night, we're going to dive into the notes on mixed precision training.
Oh, I'm looking forward to that.
Yeah, we'll explore how dropping the precision of our floating point math, moving from standard formats down to formats like bfloat16 and FP8, can magically cut our memory usage in half and double our computation speed.
That's huge.
And the best part is that strategy perfectly compounds with every single physical hardware strategy we talked about tonight.
I cannot wait to get into that one.
But, before we wrap up tonight, there's a thought from the architecture notes that's really worth mulling over.
Lay it on us.
As software engineers, we are deeply conditioned to view compute, the actual processing power, as the main bottleneck in any system.
Naturally.
But as our models continue to grow exponentially, and we keep fracturing the math across thousands of physical chips,
Yeah.
are we approaching a tipping point? Are we reaching a phase where the cost of orchestrating the communication between the GPUs actually outweighs the cost of the computation itself?
That's a scary thought.
Right. When the network becomes the computer, what happens when the network becomes the ultimate bottleneck?
That is a haunting thought to leave you with as you stare into your terminal tonight. Keep questioning the architecture behind the magic. Keep exploring the systems that make all this possible, and we will catch you back here tomorrow night for another deep dive. Stay curious.